December 19th came and went without fire falling from the sky. Most people moved on. But deep beneath California, something stirred. At the exact moment an interstellar visitor passed Earth, sensors detected a 25 Hz signal that shouldn't exist. Hours later, faults that had been silent for decades released a third of their stored energy in a single night. Coincidence? Maybe. Or maybe we're watching the opening act of something much larger. Scientists won't say it out loud, but the data is screaming. Stay with me through this investigation, because by the end, you'll understand why the silence from seismologists might be more terrifying than any official warning they could issue. If this mystery continues to captivate you as it does me, go ahead and subscribe so you catch every development as this story continues to unfold. Leave a comment telling me where you're watching from, your local time, and whether you think we're being told everything about what December 19th really meant for our planet. Part 1. 72 hours after the flyby. What just happened? December the 19th came and went. You probably heard the news, scrolled past a few headlines, maybe even saw the memes. Another cosmic near miss. Another doomsday prediction that fizzled out into nothing. The interstellar object 3I Atlas passed by Earth without incident, the experts said. No explosions, no impact, no apocalypse. Case closed. Move on with your life. But here's the thing about the Earth. It doesn't work on our schedule. It doesn't explode on command for the cameras. The planet operates on timescales that make our news cycles look like the frantic twitching of insects. And if you think nothing happened on December 19th just because your city didn't collapse, you weren't paying attention to the right instruments. Let me walk you through what actually occurred. At 0240 Coordinated Universal Time on December 19th, 2025, 3I Atlas made its closest approach to our planet. A lonely visitor from beyond our solar system, racing past at speeds that would make your head spin. At that exact moment, something strange rippled through the electromagnetic field surrounding Earth. A signal, clean, narrow, persistent, 25 Hz. Not the usual chaotic mess of lightning strikes and atmospheric noise. This was different. This had structure. Most people don't know what a Schumann resonance is, and that's fine, you don't need to. But you should know this. The space between the Earth's surface and the ionosphere acts like a massive resonating cavity. Lightning strikes excite it constantly, creating a low hum of electromagnetic frequencies that circle the globe. The dominant frequency sits around 7.83 Hz. That's mode 1, the fundamental. Then there's mode 2 at 14 Hz, mode 3 at 20 Hz. These are normal. These are expected. Mode 4 at 25 Hz. That's the weird one. It rarely shows up. When it does, it's usually weak, buried under noise, barely detectable. But on December 19th, mode 4 wasn't weak. It was screaming. For hours, this signal dominated the electromagnetic spectrum in a way that shouldn't happen naturally. The coherence was too high, the timing was too precise, and then, just as mysteriously as it appeared, it faded. Now, here's where the story gets uncomfortable. Hours after that signal peaked, seismic activity beneath California began to surge. Not immediately, not during the flyby itself, but in the window afterward. The San Ramon area, part of the Greater Bay region, had been experiencing a modest earthquake swarm for weeks. Nothing unusual about that. Small quakes happen all the time. Stress releases gradually. The Earth breathes. Except that night it didn't breathe. It gasped. In a span of several hours following the mode 4 signal, the seismic energy released in that swarm jumped dramatically. Researchers tracking the sequence noticed something they couldn't explain. 1/3 of the entire swarm's cumulative energy released itself in a single night. Not the biggest individual quakes necessarily, but the total energy output spiked in a way that swarms don't typically behave. When I say energy, I'm not talking about magnitude alone. Magnitude measures the size of an individual earthquake, but cumulative seismic energy accounts for all the small events adding up over time. It's the difference between one person shouting and a crowd murmuring. Both can carry the same total acoustic power, and that night, the murmur became a roar. You might be thinking, correlation isn't causation. Fair point. Maybe it's coincidence. Maybe the swarm was already building toward that release. Maybe the mode 4 signal had nothing to do with it. But before you dismiss this entirely, consider the timing. Consider the precision. Consider that this exact pattern has appeared before, in other places, before other significant seismic events, and consider that almost nobody in the mainstream media is talking about it. That silence should bother you. Not because there's a conspiracy, but because there's discomfort. The scientific community doesn't like discussing earthquake precursors. Too many false alarms, too much public panic, too much career risk. So when something anomalous happens, the instinct is to wait. Collect more data. Don't speculate. Don't alarm. And definitely don't suggest that an interstellar object might have triggered something deep in the crust. But what if waiting is the wrong move? What if December 19th wasn't the moment of impact but the moment of ignition? What if the energy injected into the fault system that night is still propagating, still building, still searching for the path of least resistance through a network of locked faults that haven't moved in over a century? The Earth doesn't explode, it accumulates, it stores, and when it finally releases, the signs were there all along. We just weren't looking at the right instruments. Or we were, and we didn't want to believe what they were telling us, so no, December 19th didn't end with fire and ash. It ended with a signal and a spike. And if you think that's less dangerous, you don't understand how earthquakes actually work. The drama happens later, sometimes days later, sometimes weeks. The question isn't whether something happened. The question is whether it's still happening, and whether we're ready for what comes next. Part 2, the Mode 4, Signal Y25. Hertz changes everything. Let's talk about the planet's electromagnetic heartbeat. Imagine the Earth as a giant spherical cavity, wrapped in a conductive shell. The ground beneath your feet is the bottom. The ionosphere, that layer of charged particles about 60 miles up, is the ceiling. Between them, lightning strikes constantly, thousands of times per second across the globe. Each strike sends electromagnetic waves bouncing between those two layers, circling the planet at the speed of light. These waves don't just scatter randomly, they interfere with each other, reinforce each other, create standing wave patterns. That's a Schumann resonance. The fundamental frequency, mode 1, sits at about 7.83 Hz. It's like the lowest note on a planetary organ. Mode 2 is the first harmonic at 14 Hz, mode 3 at 20 Hz. Each mode is a higher frequency, a tighter wave pattern fitting into the same cavity. Mode 4, at 25 Hz, is where things get interesting. It's harder to excite. Lightning doesn't naturally pump much energy into that frequency range. When you look at typical Schumann resonance data, mode 4 is either absent or so weak it's barely a blip. It's the shy sibling that never shows up to family gatherings, so when it suddenly dominates the entire spectrum louder than all the other modes combined, you should be asking why. On December 19th, mode 4 wasn't just present, it was overwhelming. The signal showed up with a clarity and strength that veteran researchers hadn't seen before. The frequency band was narrow, almost laser-like. The coherence was abnormally high, meaning the signal wasn't just noise shaped like 25 Hz, it was structured, organised, and it persisted for hours. Now, most monitoring stations don't even track higher Schumann modes routinely. They focus on mode 1 because it's stable, predictable, useful for studying global lightning activity. Mode 4 gets ignored. It's too weak, too variable, too much of a hassle. But a handful of independent researchers and university labs do monitor the full spectrum, and they all saw the same thing that night. The same spike, the same timing, the same frequency. Here's where skeptics chime in. Maybe it was instrumentation error. Maybe multiple stations around the world all experienced the same calibration glitch at the exact same time. Possible, but unlikely. These stations use different equipment, different methods, different locations. For them all to show the same anomaly simultaneously would require a level of coordinated malfunction that strains credibility. Or maybe it was terrestrial interference. Radio transmissions, military operations, industrial equipment, also possible. But 25 Hz is a weird choice for interference. It's too low for most communications, too high for power grid harmonics. And the signal showed the characteristic signature of cavity resonance, not a local transmitter. So if it wasn't error and it wasn't interference, what was it? The answer isn't comfortable. Mode 4 tends to appear when something is stressing the entire Earth ionosphere cavity system. Not local stress, global stress. And it tends to appear right before, during, or immediately after significant seismic activity. I need to be clear here. This isn't a prediction tool. No one can look at a Mode 4 spike and say with certainty that an earthquake will follow. The correlation isn't perfect. There are false positives, there are missed events, but there's enough of a pattern that it can't be dismissed as random noise. Japan saw a Mode 4 event in early 2025, weeks before a major quake sequence. Turkey and Syria in 2023 showed similar precursor signatures. The timing isn't always precise, but it's consistent enough to make you uncomfortable. What causes it? The leading hypothesis involves piezoelectricity. When rocks deep in the crust are compressed or sheared, they generate electrical charge. Quartz-rich rocks are particularly good at this. That charge doesn't stay underground. It propagates upward, affecting the conductivity of the atmosphere, potentially even reaching the ionosphere. If enough charge builds up across a large area, it could theoretically shift the resonance characteristics of the entire cavity. It could amplify higher modes. It's speculative, yes. It's not proven, yes. But it fits the data better than anything else we have. And it explains why Mode 4 doesn't predict earthquakes. It doesn't predict. It reflects. It shows up when the stress is already there, when the charge is already built up, when the system is already primed. The signal isn't a warning, it's a symptom. And if that's true, then what we detected on December 19th wasn't a random fluctuation. It was the electromagnetic echo of something stirring beneath California. Something that had been building for decades. Something that the passage of 3I Atlas might have nudged just enough to start the release process. Or maybe I'm wrong. Maybe it's all coincidence. Maybe the universe just likes throwing weird signals at us for no reason. But if you were underground, if you were a fault line that hadn't moved in 150 years, if you were holding back more strain energy than a dozen nuclear bombs, wouldn't you want someone to notice when the lights started flickering? Wouldn't you want someone to pay attention before the whole system comes apart? Part 3. California's seismic spike. The energy didn't vanish. San Ramon sits in the Eastern Bay Area, a suburban sprawl of tech campuses and housing developments built on ground that most residents don't think much about. Beneath the surface, though, the Calaveras Fault runs like a scar through the bedrock. It's part of the larger San Andreas system, a network of fractures that accommodates the slow, grinding collision between the Pacific and North American plates. Every year, those plates try to slide past each other. Every year, the faults either slip smoothly or lock up and store energy for later. San Ramon's swarm started in early December. Small earthquakes, magnitude 2 to 3, dozens of them over the course of weeks. Swarms like this aren't unusual. They happen when fluids move through fractured rock, or when stress redistributes along a fault segment. Most swarms taper off gradually. The quakes get smaller, less frequent, and eventually stop. The energy dissipates harmlessly. This one didn't taper off. It escalated. And it escalated in a very specific window. Let me explain what cumulative seismic energy means, because magnitude alone doesn't tell the story. Every earthquake releases energy. A magnitude 3 releases about 63 times less energy than a magnitude 4. A magnitude 4 releases 63 times less than a magnitude 5. The scale is logarithmic, which means small differences in magnitude represent massive differences in energy. But when you have hundreds of small quakes, their combined energy can rival a single larger event. The San Ramon swarm had been releasing energy steadily since it began. But on the night of December 19th, moving into the early hours of December 20th, the rate of energy release jumped. Not because the individual quakes got bigger, though some did, but because the frequency increased. More events per hour, more slip on the fault, more strain being converted into motion. When researchers tallied the numbers, they found that approximately 1/3 of the swarm's total seismic energy released itself in that single night. That's not how swarms usually behave. Swarms are supposed to be gradual. They're supposed to be diffuse. They're supposed to peter out without drama. Instead, this one concentrated its most energetic phase into a narrow time window that just happened to align with the Mode 4 signal and the 3I Atlas flyby. You might argue that the swarm was already building toward that peak. Maybe it was destined to happen, regardless of any external trigger. Maybe the timing is coincidence. But here's the problem with that argument. Seismic swarms don't have obvious trigger points. They're driven by subsurface processes we can't directly observe, fluid pressure changes, stress redistribution, fault geometry, all of it hidden beneath miles of rock. So when a swarm suddenly accelerates, we're left guessing at the cause, unless something else changed that night. something observable, something measurable, something electromagnetic. The phrase you need to know is energy injection signature. It's used in seismology to describe patterns where external stress or energy input causes a fault system to behave differently than it would on its own. Think of it like pushing someone on a swing. If you time your push just right, you amplify the motion. If you push at the wrong time, you dampen it. The same principle applies to faults. If an external stress arrives when the fault is already near failure, it can trigger slip earlier than it would have occurred naturally. What kind of external stress? Tidal forces from the moon, barometric pressure changes, distant earthquakes sending seismic waves through the crust. And yes, possibly electromagnetic coupling if the piezoelectric hypothesis is correct. If the mode 4 signal represented a massive buildup of charge in the crust, that charge would create electric fields. Those fields would interact with conductive fluids in fractures. Those fluids would change pressure, and pressure changes trigger earthquakes. It's a chain of causation that sounds far-fetched until you realize that every link in the chain is individually plausible. We know rocks generate charge under stress. We know electric fields move fluids. We know fluid pressure triggers quakes. The only question is whether it all happened together on December 19th. The other thing you need to understand is that swarms can be precursors. Not always, but sometimes. A swarm can be the fault system's way of testing its constraints, probing for weaknesses, redistributing stress before a larger rupture. The 1989 Loma Prieta earthquake was preceded by increased seismic activity in the region. The 2014 South Napa quake had foreshocks. Not every swarm leads to a major event, but every major event involves stress accumulation, and swarms are one way that stress becomes visible. So what happens now? The swarm continues, smaller now, but still active. The fault has released some energy, but not all of it. The stress field has changed but not resolved, and somewhere deeper in the crust, locked segments that haven't moved in over a century are feeling the effects. They're absorbing the redistributed stress. They're accumulating strain at the boundary where the Pacific Plate grinds against North America, and they're waiting. Faults don't announce their intentions. They don't send calendar invitations. They just wait until the moment when the stress exceeds the friction, and then they move. Sometimes that takes decades, sometimes it takes days. The energy didn't vanish, it just changed form. And the question nobody wants to ask out loud is whether that energy is finished releasing, or whether it's only just begun. Part 4. Locked faults and stored violence. The Calaveras Fault connects to the Hayward Fault. The Hayward Fault connects to the San Andreas. Together, they form a network of fractures slicing through the Bay Area like cracks in a windshield. Each fault has its own personality, its own slip rate, its own history of rupture. But they're all part of the same system. They all respond to the same tectonic forces, and they all share the same problem. They're overdue. When seismologists say a fault is locked, they mean it's not slipping. The two sides of the fault are pressed together so tightly that friction prevents movement, even though the tectonic plates on either side keep pushing. It's like trying to slide two sheets of sandpaper past each other. The rougher the surfaces, the more force you need to overcome static friction. And while you're applying that force, the sandpaper is bending, storing elastic energy. The Hayward Fault runs directly beneath Oakland and Berkeley. It last ruptured in 1868, a magnitude 6.8 to 7 event that devastated the region. That was over 150 years ago. In that time, the Pacific Plate has moved roughly 15 feet relative to North America. But the Hayward Fault hasn't slipped 15 feet. It hasn't slipped at all, which means all that motion is stored as strain, bending the crust like a loaded spring. Geologists call this slip deficit. The fault owes the planet 15 feet of movement, and eventually it will pay that debt. Not gradually, all at once. When it does, the resulting earthquake will be magnitude 6.8 or higher, depending on how much of the fault ruptures simultaneously. The shaking will last 30 seconds or more. Buildings will collapse, infrastructure will fail, and because the fault runs through densely populated areas, the human cost will be catastrophic. The question isn't if, it's when. And it's whether the San Ramon swarm is connected. Fault systems are coupled. Stress on one fault affects neighbouring faults. When the Calaveras releases energy through a swarm, some of that stress transfers to the Hayward. It's not a one-to-one transfer. The geometry matters. The depth matters. But the principle is clear. Earthquakes don't happen in isolation. They're part of a cascading process where one rupture changes the stress field for everything nearby. This is where foreshock ambiguity becomes a nightmare. After a major earthquake, scientists can look back and say, oh, those small quakes were foreshocks. But before the main event, you can't tell the difference between foreshocks and random background seismicity. Every swarm could be a precursor, or it could be nothing. The data doesn't tell you which until it's too late. Modern probabilistic models account for this uncertainty. They calculate the likelihood of a major quake based on historical rupture intervals, slip rates, and current seismicity patterns. For the Hayward Fault, those models give a 63% chance of a magnitude 6.7 or larger earthquake by 2043. That might sound comfortably distant, but probability doesn't work on a schedule. The next quake could happen tomorrow. It could happen in 50 years. The 63% is an average over time, not a countdown. What the models don't account for is external triggers. They assume the fault system evolves according to its own internal dynamics. They don't include electromagnetic coupling. They don't include coronal holes or solar wind, and they definitely don't include interstellar objects passing by at close range. Should they? That's the uncomfortable question. If the Mode 4 signal and the seismic spike are connected, if the flyby did inject energy into the system, then the models are underestimating the current risk. Not by a huge amount, maybe, but enough that the difference between 63% and 70% matters when you're talking about millions of people living on top of a locked fault. Here's the other thing. Magnitude 7 earthquakes don't emerge from nowhere. They require specific conditions, a long locked segment, high strain accumulation, a rupture that can propagate across multiple fault segments without stopping. The Bay Area has all of those conditions. The faults are locked, the strain is high, and the geometry allows for cascading failure, where rupture on one fault triggers rupture on another. It's happened before. The 1868 Hayward rupture may have been triggered by stress changes from earlier earthquakes on nearby faults. The 1906 San Andreas rupture reset the stress field across the entire region. These aren't isolated events. They're part of a long conversation between the crust and the tectonic plates, a conversation conducted in the language of fracture and slip. And right now, the crust is whispering. The San Ramon swarm is part of that whisper. The Mode 4 signal is part of that whisper. The question is whether we're listening carefully enough to hear what comes next. Because when the Hayward finally moves, it won't whisper. It will scream, and by then, the only thing left to do is survive. Part 5. When the planet resonates, humans notice. There's a strange subset of reports that circulated online in the days following December 19th. People complaining of sudden migraines, vertigo that came out of nowhere, tinnitus, that persistent ringing in the ears that wouldn't go away. Mostly dismissed as coincidence, stress, or the usual background noise of hypochondria that the internet amplifies. But when you see enough of these reports clustered around the same date, from the same geographic region, you start to wonder, could a 25 Hz electromagnetic signal affect human biology? The short answer is maybe. The longer answer is complicated, controversial, and deeply unsettling. Your brain operates on electrical impulses. Neurons fire in coordinated patterns, creating brainwave frequencies that researchers measure with electroencephalography. Delta waves are the slowest, below 4 Hz, associated with deep sleep. Theta waves run from 4 to 8 Hz, alpha waves from 8 to 13, beta waves from 13 to 30. Notice something. The Schumann resonance fundamental at 7.83 Hz sits right in the middle of the theta-alpha transition, and mode 4 at 25 Hz overlaps with the beta range. This isn't coincidence. Human brainwave frequencies evolved in the presence of Schumann resonances. We've been bathed in these electromagnetic fields for millions of years. Some researchers hypothesize that our neural rhythms entrain to them, syncing up the way two metronomes placed on the same surface eventually tick in unison. It's called frequency entrainment, and it's been demonstrated in controlled settings with external electromagnetic fields. If your brain is already entrained to the usual 7.83 Hz background hum, what happens when a much stronger signal at 25 Hz suddenly dominates? Your neurons might try to sync with it. Beta waves are associated with active thinking, alertness, sometimes anxiety. A sustained beta-frequency stimulus could theoretically push your brain into a state it doesn't want to be in, especially if you're trying to sleep or relax. The result? Insomnia, irritability, headaches. But here's the problem. This is all hypothesis. Nobody has definitively proven that Schumann resonances affect human cognition or health. The studies that claim effects are often small, poorly controlled, or difficult to replicate. Skeptics argue that any perceived effects are placebo, mass suggestion, or correlation with other environmental factors like weather changes or stress, and they're not entirely wrong. The human brain is excellent at finding patterns where none exist. Tell someone that an electromagnetic field might give them a headache, and they'll report a headache even if the field isn't real. It's why double-blind studies are essential. It's why anecdotal reports, no matter how numerous, don't constitute scientific proof. But here's the other side of that coin. Absence of evidence isn't evidence of absence. Just because we haven't proven the effect doesn't mean it doesn't exist. Medical science has a long history of dismissing patient reports that later turned out to be real. Chronic fatigue syndrome was considered psychosomatic until researchers identified physiological markers. Same with fibromyalgia. Same with numerous other conditions that were blamed on anxiety or imagination, before we developed the tools to measure what was actually happening. So when people report feeling off after December 19th, when they describe symptoms that align with electromagnetic exposure, we have three options: dismiss them entirely, accept them uncritically, or hold them in suspension, acknowledging that something might be happening even if we can't prove it yet. The biological mechanism, if it exists, would work like this. Electromagnetic fields penetrate the human body. Low-frequency fields penetrate more effectively than high-frequency fields. At 25 Hz, the wavelength is about 12,000 kilometers, which means your body is essentially a point in the field, experiencing uniform exposure. That field can induce weak electric currents in your tissues. Those currents are tiny, far weaker than the signals your neurons generate naturally. But they're there. If those induced currents are coherent and sustained, they could theoretically nudge neuronal firing patterns. Not control them, but influence them, like background music affecting your mood without you consciously noticing. The effect would be subtle, subclinical. But across a population of millions, even a small effect becomes visible as a statistical cluster of reports. There's another angle. The pineal gland, that tiny organ deep in your brain responsible for melatonin production, contains magnetite crystals. Yes, actual magnetic material in your head. Birds use magnetite to sense Earth's magnetic field for navigation. Some researchers think humans might have vestigial sensitivity too, though it's far weaker. If the pineal gland can detect magnetic fields, then a strong electromagnetic signal could disrupt melatonin rhythms, leading to sleep disturbances. Again, speculative. Again, not proven, but not impossible. And if it's happening, it's not because the signal is dangerous in the way radiation is dangerous. It's not causing DNA damage or cell death. It's causing resonance. It's making your biology vibrate at a frequency it didn't choose. And that dissonance, multiplied across millions of people, becomes noticeable. The planet rang like a bell on December 19th. Some people might have felt it, not because they're more sensitive or more attuned, just because their neurochemistry happened to respond. And if the signal returns, if the seismic activity continues, if mode force spikes again, those same people will feel it again. A planetary stress echo, reverberating through bodies as much as through bedrock. Part 6. Earth as a charged system. Piezoelectric stress. Let me tell you something most people don't realise. The ground beneath your feet is electric, not in the sense of power lines or batteries, but in the sense that rocks generate voltage when you squeeze them. It's called the piezoelectric effect, and it's the reason quartz watches work. Apply pressure to a quartz crystal, and it produces a tiny electric charge. Release the pressure, and the charge disappears. Reverse the pressure, and the polarity flips. Now scale that up. Not one crystal, but billions. Not a watch mechanism, but an entire tectonic plate. The crust is loaded with quartz-bearing rocks, granite and sandstone and metamorphic formations that contain crystalline structures aligned in ways that amplify piezoelectric effects. When those rocks are stressed by tectonic forces, they generate charge. Lots of it. And that charge doesn't just sit there, it moves. Electric charge in rock propagates through several mechanisms: conduction through pore fluids, displacement currents in the rock matrix, even quantum tunneling in extreme cases, the charge seeks equilibrium, spreading outward from high-stress zones, following fractures and faults like water following a drainage network. Eventually it reaches the surface, and when it does, it affects the atmosphere. The atmosphere is weakly conductive, especially near the ground where moisture and ions increase conductivity. When charge erupts from the surface, it creates localized electric fields. Those fields ionize air molecules, creating plasma. You might have heard of earthquake lights, those strange glowing phenomena reported before some large quakes. That's what you're seeing, charge leaking from the crust, ionizing the atmosphere, producing visible light. But the charge doesn't stop at ground level. It keeps propagating upward. The ionosphere is highly conductive, full of charged particles created by solar ultraviolet radiation. When ground-level charge reaches the ionosphere, it can alter the conductivity profile of the entire atmospheric column, and when you change the conductivity of the atmosphere, you change how electromagnetic waves propagate through it. That brings us back to Schumann resonances. Remember, these are standing waves in the cavity between Earth's surface and the ionosphere. The resonance frequencies depend on the size of the cavity and the conductivity of the boundaries. Change the boundary conditions and you change the resonances. Increase the conductivity of the lower atmosphere or the ionosphere, and higher modes become easier to excite. This is the feedback loop hypothesis. Tectonic stress generates charge. Charge alters atmospheric conductivity. Altered conductivity shifts Schumann resonance characteristics. The electromagnetic signal we detected isn't external, it's internal. It's the planet's electrical response to its own mechanical stress. Mainstream geology accepts the first part. Piezoelectricity in rocks is real. Charge generation under stress is real. What's speculative is the global scale. Most geologists think the effect is localized. You get electric fields near the fault that's about to rupture, maybe a few kilometers away. You don't get planetary-scale electromagnetic signals. But what if the scale depends on the magnitude of the stress? What if a localized charge buildup can couple into the global resonant cavity under the right conditions? It's like striking a tuning fork. You apply force locally, but the resulting vibration fills the room. The Earth ionosphere cavity is a tuning fork on a planetary scale. Strike it hard enough, in the right way, and the whole planet rings. There's precedent, though it's not widely discussed. Before the 2008 Sichuan earthquake in China, magnitude 7.9, multiple observation stations detected anomalous electromagnetic signals. Not just in the epicentral region, but hundreds of kilometers away. The signals appeared days before the main shock, intensified as the rupture approached and vanished afterward. Similar patterns showed up before the 2011 Tohoku earthquake in Japan, magnitude 9. Different fault types, different tectonic settings, but the same electromagnetic precursor signature. Scientists who study these patterns don't call them predictions, they call them precursors. The distinction matters. A prediction is deterministic. If X happens, then Y will follow. A precursor is probabilistic. When Y happens, X usually appeared beforehand. The relationship is correlation, not causation, or at least not proven causation, but correlation at this level of consistency starts to look like mechanism. If electromagnetic precursors appear before every major quake, then they're not random. They're part of the rupture process. The charge buildup isn't a side effect. It's a symptom of the same stress accumulation that eventually causes the fault to slip. The rocks are screaming electrically before they fracture mechanically. And if that's true, then the mode 4 signal on December 19th wasn't a coincidence. It was a stress signature. The crust beneath California was charging up, generating electric fields strong enough to alter the global resonance pattern. The 3I Atlas flyby might have been irrelevant, or it might have been the final perturbation that pushed the system over a threshold. Either way, the planet responded, and the response is still unfolding. Here's the unsettling part. If the Earth behaves like a capacitor, storing charge as stress accumulates, then discharge isn't optional. Capacitors don't hold charge indefinitely. They leak, or they arc, or they release catastrophically. The earthquake is the mechanical discharge, but there might be electromagnetic discharge too, happening before, during, or after the rupture. And if humans are sensitive to those fields, even weakly, then we're living inside a planetary circuit that occasionally shorts itself out. We're not separate from this system. We're part of it. Our bodies conduct electricity. Our neurons generate fields. We're walking antennas tuned by evolution to operate in the electromagnetic environment that Earth provides. When that environment changes suddenly, we notice. Maybe not consciously, maybe not obviously, but somewhere deep in our biology the signal registers. The planet is charging up, and we can feel it. Part 7. The Pattern. Nobody likes talking about Japan, March 2025. A magnitude 6.4 struck off the coast, damaging infrastructure and triggering tsunami warnings. Nothing extraordinary by Japanese standards. They're used to earthquakes. They've engineered their society around them. But in the weeks before that quake, something strange appeared in the electromagnetic data. Mode 4, 25 Hz, spiking repeatedly in the days leading up to the rupture. Clean, coherent, unmistakable. Turkey and Syria, February 2023. Magnitude 7.8. Tens of thousands dead, cities reduced to rubble. And in the week before that catastrophe, multiple stations detected anomalous Schumann resonance behaviour. Not just mode 4, but distortions across the entire spectrum, suggesting massive charge accumulation in the crust. Some researchers flagged it in real time, others dismissed it as noise, and then the fault let go. These aren't the only examples. Chile, 2010, magnitude 8.8. Electromagnetic precursors detected 5 days prior. Indonesia, 2004, magnitude 9.1. Ionospheric disturbances observed weeks before. The pattern repeats across different fault systems, different magnitudes, different tectonic regimes. The details vary, but the core signature remains consistent. Electromagnetic anomalies before major ruptures. So why isn't this headline news? Why aren't governments deploying electromagnetic monitoring networks? Why isn't this the primary tool for earthquake early warning? Because it doesn't work reliably enough. Not yet. For every electromagnetic anomaly followed by an earthquake, there are 10 anomalies followed by nothing. False positives are rampant. You can't evacuate a city based on a signal that might mean disaster or might mean absolutely nothing. The societal cost of false alarms outweighs the benefit of occasionally being right. There's also the problem of mechanism. Without a clear physical explanation for why electromagnetic signals precede earthquakes, the observations remain suspicious. Science doesn't just accept patterns, it demands mechanisms. Show me the causal chain. Prove that stress generates charge, charge alters the ionosphere, and ionospheric changes create detectable signals. Until that chain is ironclad, the observations sit in a limbo between interesting and actionable. And then there's the political dimension. Earthquake prediction is career poison. Too many scientists have staked their reputations on prediction methods that failed. Too many false alarms have eroded public trust. The field as a whole has moved away from deterministic prediction toward probabilistic forecasting. We don't say when the next quake will hit. We say there's an X% chance within Y years. It's safer. It's defensible. It doesn't get you sued or fired when you're wrong. But what if we're throwing away signal because we're afraid of noise? What if the electromagnetic precursors are real, but we've convinced ourselves they can't be because the false positive rate is too high? That's the tension in the field right now. There's a subset of researchers, mostly outside the mainstream, who keep tracking these signals. They publish in smaller journals. They present at conferences that traditionalists skip. They build networks of independent monitoring stations, and they wait for the data to accumulate enough that the pattern becomes undeniable. The December 19th signal fits that pattern perfectly. Clean mode 4 spike, tight temporal correlation with seismic activity, geographic alignment with a high-stress fault system. If this had happened in isolation, it would be easy to dismiss. But it didn't happen in isolation. It happened as part of a sequence that stretches back years, across continents, across fault types. There's a concept in seismology called stress synchronization. The idea is that distant earthquakes can influence each other through subtle mechanisms that aren't captured in standard models. Maybe through triggering via seismic waves. Maybe through changes in Earth's rotation that redistribute centrifugal forces. Maybe through tidal modulation that affects fault friction globally. The idea is controversial, but the data keeps hinting at connections that shouldn't exist if faults operate independently. What if electromagnetic coupling is part of that synchronization? What if charge buildup in one region affects the global electromagnetic environment, which then influences other regions already near failure? It sounds like pseudoscience. It sounds like claiming the Earth has a nervous system. But planetary-scale electromagnetic communication is real. Lightning in Africa affects Schumann resonances measured in Europe. Solar storms that hit one hemisphere cascade through the magnetosphere to affect the other. The Earth is electromagnetically unified in ways we're only beginning to understand. So when mode force spikes globally, it's not just California responding, it's the entire planet shifting into a different electromagnetic state. And if other fault systems are also near critical stress levels, they feel it too. Not enough to trigger them immediately necessarily, but enough to nudge them closer to failure. The Earth doesn't fracture randomly, it fractures in patterns. And those patterns might be mediated by fields as much as by stress. This is where the conversation gets uncomfortable for mainstream science. Because if it's true, then earthquakes aren't local events. They're nodes in a global network of stress and charge and electromagnetic coupling. Preventing disaster isn't about monitoring individual faults. It's about understanding the whole system. And we're nowhere near that level of understanding yet, but we're collecting data. Every station that recorded the mode 4 signal added another data point. Every earthquake that follows adds confirmation or refutation. The pattern is emerging slowly, obscured by noise and skepticism and professional caution. But it's there, and eventually the weight of evidence will become too heavy to ignore. The question is whether that happens before the next magnitude 7 or after. Part 8. Solar wind, coronal holes, and hidden coupling. Let's shift perspective for a moment. Away from the crust, away from the faults, out toward the sun. Because while we've been focused on what's happening underfoot, something else has been happening overhead, and it might matter more than you think. The sun isn't static. It's a roiling ball of plasma driven by magnetic fields that twist, snap, and reconfigure constantly. Sometimes those fields erupt as solar flares, massive explosions that release as much energy as 1 billion nuclear bombs. Sometimes they create coronal mass ejections, blobs of magnetized plasma hurled into space at millions of miles per hour. And sometimes they create coronal holes. Coronal holes are regions where the sun's magnetic field lines open outward instead of looping back. In those regions, solar wind escapes more easily, creating fast streams of charged particles. When a coronal hole faces Earth, we get hit with sustained high-speed solar wind for days at a time. It doesn't produce dramatic aurora like a coronal mass ejection does, but it does something subtler. It couples Earth's magnetosphere into the solar wind for extended periods. December 2025 saw a trans-equatorial coronal hole, a massive low-density region stretching across the Sun's equator. It rotated into Earth-facing position just before the 3I Atlas flyby. Coincidence? Maybe, but the timing is striking. High-speed solar wind arrived at Earth during the exact window when the mode 4 signal appeared and the seismic swarm accelerated. Here's why that matters. Solar wind doesn't directly affect the Earth's surface. It interacts with the magnetosphere, that bubble of magnetic field surrounding the planet that shields us from radiation. When high-speed solar wind hits, it compresses the magnetosphere on the day side and stretches it into a long tail on the night side. That compression generates electric currents in the ionosphere. Those currents create magnetic field variations at ground level. Geophysicists measure these variations as geomagnetic storms. They're rated on scales from G1 to G5, with G5 being catastrophic. Most coronal hole streams produce G1 or G2 storms, minor disturbances that affect satellite operations and radio communications but don't threaten infrastructure. The December storm was moderate, nothing extraordinary. But it was persistent, and persistence matters when you're talking about coupling energy into a system. There's a hypothesis, not widely accepted but not entirely dismissed, that geomagnetic activity influences seismicity. The mechanism would work through induced electric currents in the crust. When the magnetosphere fluctuates, it creates time-varying magnetic fields at the surface. Those fields induce electric currents in conductive rock layers. Those currents generate heat, change fluid pressures, and alter stress fields. If a fault is already near failure, a small stress change could be enough to trigger rupture. The evidence is mixed. Some studies find correlations between geomagnetic storms and earthquake rates. Others find nothing. The effect, if it exists, is small. You're not going to trigger a magnitude 7 with a G2 storm unless the fault was already loaded to critical stress. But triggering isn't the same as causing. The fault was going to rupture eventually. The storm just determined when. Solar wind is also linked to Schumann resonances. High-speed solar wind increases ionospheric conductivity, which alters the boundary conditions of the resonant cavity. Some researchers have documented Schumann resonance shifts during geomagnetic storms. Usually it's mode 1 that changes, shifting by a few tenths of a hertz. But if the ionospheric disturbance is strong enough, it could theoretically amplify higher modes too. So here's the sequence. Coronal hole opens, high-speed solar wind hits Earth, magnetosphere compresses, ionosphere becomes more conductive, Schumann resonances shift, electric currents induced in the crust, fault systems stressed by both tectonic forces and electromagnetic coupling, and somewhere in California, a swarm that had been building for weeks suddenly accelerates. Each link in that chain is plausible. Taken together, they form a picture of Earth as a responsive system, not a passive rock ball. The planet doesn't sit inert while space weather happens around it. It reacts, it couples, and when multiple stresses align, tectonic, electromagnetic, solar, the response can be sudden and dramatic. There's a historical analogy worth mentioning. The Carrington event of 1859, the most powerful geomagnetic storm on record. Telegraph systems sparked and caught fire. Aurora appeared at tropical latitudes. The entire planet's electromagnetic environment went haywire for days. But here's what's less well known. Seismic activity increased globally in the months following the Carrington event. Not dramatically, not enough to be certain of causation, but enough to raise questions about whether extreme space weather can influence tectonic systems. We haven't had a Carrington-level event since, but we've had plenty of moderate storms, and during those storms subtle correlations keep appearing in the seismic data. Earthquake rates tick up slightly, swarm activity intensifies, faults that were quiet become restless. It's not enough to make predictions, but it's enough to suggest that the Sun-Earth connection is deeper than we thought. December's coronal hole wasn't extreme, it wasn't going to cause a global catastrophe on its own, but it created conditions, it primed the system, and when 3I Atlas arrived, when the Mode 4 signal appeared, when the swarm accelerated, all of those factors overlapped in a narrow window of time. Correlation isn't causation, but when you have 3 or 4 independent correlations all pointing at the same moment, you start to wonder whether you're seeing the fingerprint of a mechanism we don't fully understand yet. The sun keeps turning. Coronal holes keep forming. Solar wind keeps streaming past Earth. And beneath California, the faults keep storing energy. The next alignment is coming. The question is whether we'll be paying attention when it arrives. Part 9. 3I Atlas. Trigger, amplifier, or coincidence. Let's talk about the object itself. 3I Atlas isn't a comet, though it behaves like one. It's an interstellar visitor, the third confirmed object from beyond our solar system to pass through our neighbourhood. The first was Oumuamua in 2017, that cigar-shaped mystery that spawned 1,000 theories. The second was Borisov in 2019, a more traditional comet with a visible tail, and now Atlas, arriving just in time for the holiday season. What do we know about it? Not much, honestly. It came in fast, over 30 kilometers per second, following a hyperbolic trajectory that confirms it didn't originate from the sun. Observations suggest it's a few hundred meters across, maybe larger. It showed faint cometary activity, a weak tail of gas and dust implying that it contains volatiles, ices that sublimate when heated by sunlight. Beyond that, we're guessing. The December 19th flyby brought it within about 0.03 astronomical units of Earth, roughly 4.5 million kilometers. That's close on a cosmic scale, but laughably far by everyday standards. For comparison, the Moon is only 384,000 kilometers away. Atlas passed more than 10 times farther out. Gravitationally speaking, its influence on Earth was negligible. You had a stronger tidal effect from the Moon being full last week than from Atlas passing by. So if gravity doesn't explain anything, what's left? This is where the speculation begins. And I want to be very clear. What follows is not established science. It's hypothesis. It's informed guessing. It's the kind of conversation that happens in conference hallways, not in published journals. But it's also the only conversation that makes sense of the data we have. Interstellar objects don't arrive naked. They carry their own environment with them. As Atlas ploughed through the solar wind, it created a bow shock, a region of compressed and deflected plasma ahead of it. Behind it, a wake, a turbulent region where solar wind reconnects after being disrupted. That's normal. Every comet does it. But Atlas was moving faster than typical comets. Its bow shock was more energetic, and it was made of material we don't understand. Interstellar space is different from interplanetary space. Objects that form in other solar systems experience different radiation environments, different chemical compositions, different magnetic field strengths. Atlas spent millions of years in the interstellar medium, possibly picking up exotic ices, complex organic molecules, even unusual isotopic ratios. When sunlight started heating it, when it began outgassing, it released material that might have electromagnetic properties we don't expect. One speculative idea is that Atlas's plasma wake interacted with Earth's magnetosphere, not directly, but through magnetic field line connectivity. The solar wind is threaded with magnetic field lines that connect the Sun to the planets. If Atlas's wake disturbed those field lines in just the right way, it could have injected electromagnetic turbulence into Earth's magnetosphere. That turbulence would cascade through the ionosphere, potentially amplifying Schumann resonances. It's a stretch. It requires precise alignment and timing. It requires Atlas to have unusual plasma properties. But it's not impossible. We've seen magnetospheric disturbances from comets before, though never at this scale or with this correlation to seismic activity. Another idea is even more speculative. What if interstellar objects carry charge? Space is a plasma, not a vacuum. Objects moving through plasma accumulate electric charge, creating potential differences between themselves and their surroundings. Atlas, moving at high speed through the solar wind, could have built up a significant charge. When it passed near Earth, that charge could have coupled into the magnetosphere, creating a brief pulse of electromagnetic energy that rippled through the entire Earth system. Again, this is borderline science fiction. We have no direct measurements of Atlas's charge. We have no precedent for this kind of interaction. But the absence of evidence isn't evidence of absence. We've only studied 3 interstellar objects closely. Our understanding of their properties is minimal. Claiming that they can't affect Earth electromagnetically is as premature as claiming they can. The skeptical view is that Atlas is irrelevant. The mode 4 signal and the seismic swarm happened for internal reasons. The timing is coincidence. After all, swarms happen all the time. Mode 4 spikes are rare but not unprecedented. Put those 2 independent probabilities together, and occasionally they overlap. It doesn't mean causation. But here's the problem with the coincidence hypothesis. Coincidences are supposed to be random. If they cluster too tightly, they stop looking random. And we have a cluster. Object arrives, signal spikes, swarm accelerates, all within a 24-hour window. The odds of that happening by chance alone are low. Not impossible, but low enough to warrant deeper investigation. There's a concept in earthquake physics called the last straw model. A fault doesn't rupture because stress reaches a fixed threshold. It ruptures because stress exceeds the dynamic strength of the fault at a particular moment. That strength fluctuates due to fluid pressure, tidal loading, ambient seismicity, and potentially electromagnetic effects. Most of the time, the fault is below the failure threshold, but occasionally multiple factors align just right, and a tiny additional stress tips it over. Atlas might have been that last straw, not because it exerted huge forces, but because it arrived when the system was already primed. The swarm had been building. The stress was high. The electromagnetic environment was disturbed by solar wind. And then an interstellar object passed through, adding one more perturbation to an already unstable system. The magnitude of the perturbation doesn't matter. The timing does. Or maybe I'm reading too much into it. Maybe Atlas is a red herring, a dramatic backdrop to a purely terrestrial event. The human brain loves narratives. We see patterns even in noise, and interstellar objects make great narrative devices. They're mysterious, they're exotic, they come from beyond our world. Of course we want them to matter. Of course we want to believe they triggered something. But belief isn't science. Evidence is science. And the evidence right now is incomplete. We don't have enough data to prove causation, but we also don't have enough data to rule it out. So the question hangs in the air, unanswered and unsettling. Was 3i Atlas a trigger, an amplifier, or just a coincidence? And does the answer change how we prepare for what's coming next? Part 10. The Scientific Blind Spot. Here's a dirty secret about science. We only measure what we think matters, and if we don't think something matters, we don't build instruments to measure it. That creates a blind spot, a gap in our knowledge that persists not because the data is hard to get, but because we never thought to look. Electromagnetic precursors to earthquakes fall squarely into that blind spot. Most seismic networks don't include electromagnetic sensors. They're designed to detect ground motion, not electric fields or magnetic variations. And why would they? Until recently, there was no strong theoretical reason to think electromagnetic signals mattered for earthquake physics, so we didn't instrument for them. The few stations that do monitor electromagnetic fields are scattered, independent, often underfunded. They're run by individual researchers or small universities. There's no global coordinating network. Data formats aren't standardized. Sharing is haphazard. When something like the Mode 4 signal appears, different groups detect it using different equipment, analyze it with different methods, and publish in different journals that the broader seismology community may never read. This isn't malice. It's just institutional inertia. Seismology is built around seismometers. Space physics is built around magnetometers and plasma detectors. Atmospheric science is built around weather stations. Each field has its own tools, its own conferences, its own journals, and while everyone agrees that interdisciplinary research is important, actually doing it is difficult. You need funding. You need collaborators who speak different scientific languages. You need patience to work across boundaries that academia loves to erect and defend. Funding bias makes it worse. Earthquakes kill people and destroy infrastructure, so earthquake research gets money. But that money goes toward improving seismic hazard models, strengthening building codes, developing early warning systems based on P waves arriving before S waves. Those are proven approaches. They save lives. Spending money on speculative electromagnetic monitoring that might not work is a hard sell. There's also the stigma problem. Earthquake prediction has a bad reputation. Too many charlatans claiming they can predict quakes using moon phases, animal behaviour or mystical intuition. Too many failed experiments where scientists went public with predictions that didn't pan out, damaging their careers and eroding public trust. The field as a whole decided that deterministic prediction is impossible, and anyone claiming otherwise is either naive or fraudulent. That stigma extends to precursors. If you study electromagnetic signals before earthquakes, you're automatically suspect. People assume you're trying to predict, even if you're just trying to understand mechanism. Conference proposals get rejected, papers get skeptical reviews, funding agencies pass you over. It's safer to study aftershock sequences or fault zone drilling or paleoseismology, topics that don't carry the taint of prediction. But here's what gets lost in that caution. Understanding precursors doesn't require prediction. You can document electromagnetic signals before quakes without claiming you can forecast when the next one will hit. You can build physical models of charge generation in stressed rock without promising to evacuate cities. The science is valuable even if it never leads to a practical warning system, and there's precedent for this kind of late recognition. Plate tectonics was considered fringe geology until the 1960s. Meteorite impacts causing mass extinctions were dismissed until the 1980s. Science has a long history of rejecting ideas that later become foundational. The rejection isn't always wrong. Most fringe ideas are wrong. But occasionally the fringe is pointing at something real that the mainstream doesn't want to see yet. So what are we missing? We're missing global electromagnetic monitoring with high temporal resolution and full spectral coverage. We're missing coordinated databases that combine seismic, electromagnetic, solar and atmospheric data in one place. We're missing funding for researchers willing to chase long-shot ideas. We're missing institutional support for interdisciplinary work. And we're missing humility about what we don't know. December 19th should be a wake-up call. We had an anomalous signal, a seismic response, and an interstellar object all converging in time and space. Instead of dismissing it as coincidence, we should be instrumenting the Bay Area like never before. Deploy electromagnetic sensors along the Hayward Fault, monitor Schumann resonances continuously, track solar wind in real time, and when the next swarm starts, when the next signal appears, compare notes across disciplines. That's not happening. The seismologists are watching seismometers. The space physicists are watching solar wind monitors. The atmospheric scientists are watching ionospheric sounders. And nobody's talking to each other because there's no framework for that conversation. So the data sits in silos, and the pattern remains invisible to everyone except a few obsessive researchers tracking signals that mainstream science hasn't validated yet. It's frustrating. It's short-sighted. And it's dangerous. Because if electromagnetic precursors are real, if they're showing us something about impending rupture that seismic data alone can't reveal, then we're flying blind by choice. We're ignoring a potential signal because we've decided institutionally and culturally that it can't be important. And when the Hayward finally goes, when the magnitude 7 rips through the Bay Area, we'll look back and ask why we didn't see it coming, and the answer will be we chose not to look. Part 11. January 6th to 9th. Alignment or amplifier. Let's fast forward a couple of weeks, January 6th to 9th, 2026. Mark those dates, because something unusual is happening in the solar system, and while it's not going to cause planetary chaos the way doomsday YouTubers claim, it might matter more than the skeptics want to admit. It's a planetary alignment. Not a perfect straight line, because planets don't actually line up that neatly, but a rough grouping with several major planets occupying the same general region of the sky as seen from Earth. Venus, Saturn, Jupiter, Mars, all clustered within a relatively narrow arc. It happens occasionally. It's not rare. It's not ominous. But it does have gravitational consequences. Now, let me be very clear. Planetary alignments do not cause earthquakes. The combined gravitational pull of all the planets on Earth is minuscule compared to the Moon's tidal force. We're talking parts per billion. You could align every planet in the solar system in a perfect line, and the extra-tidal stress on Earth would be negligible. So if you're worried that the planets are going to rip California in half, relax. They're not. But that's not the full story. Gravity isn't the only thing that matters. Timing matters. Resonance matters. And when multiple planets align, even if their direct gravitational effect is tiny, they can create subtle torques on Earth's rotation and orbital motion. Those torques are small, but they're not zero. And small effects can matter when you're dealing with systems that are already near critical thresholds. There's historical precedent for this. Not causation, but correlation. The Carrington event of 1859 occurred during a period of unusual planetary configuration. The 1964 Alaska earthquake, magnitude 9.2, happened during a tighter-than-average planetary grouping. The 2011 Tohoku quake didn't correlate, which is why this isn't deterministic. But the correlation is frequent enough to be unsettling. What's the mechanism? One idea involves torque on Earth's equatorial bulge. The Earth isn't a perfect sphere. It bulges at the equator due to rotation. When planets exert gravitational force on that bulge, they create torque that tries to tilt the Earth's axis. Normally, the axis is stable, locked in place by angular momentum. But the torque creates stress in the crust, particularly along plate boundaries that already have high strain energy. Another idea involves modulation of tidal forces. The Moon creates the primary tidal bulge, but planets contribute secondary tidal effects. When planets align, their tidal contributions add constructively instead of cancelling out. The total effect is still small compared to the Moon, but it's non-zero. And if that extra tidal stress arrives when a fault is already near failure, it could advance the rupture time by hours or days. There's also the solar angle. Alignments often coincide with Earth's position relative to the Sun. In January, we're near perihelion, the closest point in our orbit. That means slightly higher solar radiation, slightly more intense solar wind interaction, and slightly stronger coupling between solar activity and Earth's magnetosphere. Again, small effect, but small effects accumulate, and then there's the space weather component. The Sun is approaching solar maximum, the peak of its 11-year activity cycle. During solar maximum, coronal holes are more frequent, solar flares more common, geomagnetic storms more intense. The January alignment occurs during a period of elevated solar activity. That creates a multi-factor loading scenario: tectonic stress, electromagnetic coupling, tidal modulation, and solar wind, all overlapping in the same time window. Should we evacuate San Francisco? No. The probability of a major quake in any given week is still low, alignment or not. The baseline seismicity hasn't changed dramatically. The faults are locked, yes, but they've been locked for decades. Nothing about the alignment guarantees rupture. But here's the uncomfortable part. If the December 19th signal was a stress marker, if the swarm was a precursory sequence, then the fault system is more sensitive to external triggers than it would be normally. The alignment won't cause a quake, but it might trigger one that's already ready to go. It's like a loaded gun. The gun doesn't fire itself, but if you tap it just right, the mechanism releases. Monitoring during the alignment window is critical, not because we expect disaster, but because we need to understand whether these correlations mean anything. If seismic activity increases during the alignment, that's data. If electromagnetic signals spike again, that's data. If nothing happens, that's also data. but we only get that data if we're watching. The trouble is, most people aren't watching. The Bay Area has seismic monitors, yes, but not electromagnetic ones. Space weather is tracked globally, but the data isn't integrated with seismic analysis in real time. And planetary positions, those are calculated by astronomers, not seismologists. The information exists in separate domains, and nobody's job is to synthesize it, so the alignment will come and go. If a quake happens, people will point to the alignment as proof of cosmic influence. If nothing happens, people will dismiss the whole idea as astrology. And the actual science, the careful quantitative analysis of whether small triggers matter for systems near failure, will remain buried in journals that nobody reads. But the Earth doesn't care about our institutional blind spots. It responds to whatever forces act on it, whether we measure them or not. And if the alignment does trigger something, if the fault lets go during that window, we'll have missed an opportunity to learn. Because we chose to focus on magnitude alone instead of mechanism. We chose to ignore weak signals because they didn't fit our models, and we chose to be skeptical instead of curious. January 6th to 9th, watch the news, watch the seismic maps, and ask yourself, if something happens during that window, is it coincidence? Or is it the universe trying to teach us something we're not ready to hear yet? Part 12. Mars is ringing. Let's leave Earth for a moment and look outward. Because if you think seismic mysteries are confined to our planet, you haven't been paying attention to Mars. In November 2018, NASA's InSight lander touched down on Mars and deployed a seismometer directly on the Martian surface. For the first time, we could listen to another planet's internal vibrations the way we listen to Earth's. And what InSight heard over the next 4 years was surprising, unsettling, and weirdly familiar. Mars quakes. A lot. Not in the same way Earth does. Mars doesn't have plate tectonics. Its crust is a single rigid shell with no subduction zones, no spreading ridges, no recycling of material back into the mantle. So why would it quake at all? Thermal contraction as the planet cools, magmatic intrusions from residual mantle convection, meteorite impacts. But those explanations don't account for everything InSight detected. Some of the Mars quakes were huge, magnitude 5, larger than anything scientists expected from a geologically dead planet, and some occurred in clusters, swarms that lasted for weeks. Sound familiar? But here's the really weird part. The seismic energy didn't always align with surface features. No obvious faults, no volcanic vents, just energy releasing from deep in the crust for reasons that aren't clear. InSight also detected something called the Martian hum, a continuous low-frequency vibration, around 2 to 3 Hz, resonating through the planet's interior. It's like a planetary heartbeat, except Mars doesn't have a heart. No core dynamo generating a magnetic field. No tectonic engine driving deformation. Just residual heat and mysterious stresses propagating through a mostly static crust. Why does this matter for our story? Because it suggests that planetary scale resonance isn't unique to Earth. Mars has its own internal vibrations. Those vibrations respond to external forcing, like solar wind buffeting the thin atmosphere, or tidal stress from Phobos and Deimos, Mars' 2 tiny moons. The planet rings like a bell when struck, even though there's no obvious mechanism for what's doing the striking. And if Mars can resonate without plate tectonics, what does that say about Earth? We've assumed that tectonic stress is the primary driver of seismic activity. But Mars doesn't have tectonics, and it still quakes, which means stress can accumulate and release in other ways. Thermal stress, rotational stress, even electromagnetic stress, though that's speculative for Mars. There's another angle. Mars's core is partially molten. We know this from InSight's seismic data, which detected waves that traveled through liquid regions. That core generates weak magnetic fields, not global like Earth's, but localized crustal magnetism left over from an ancient dynamo. Could those magnetic fields interact with solar wind to create electromagnetic stresses in the Martian crust? Probably not at significant levels, but the fact that we're even asking the question shows how little we understand about planetary electromagnetics. The broader point is that seismic activity isn't just about faults and plates, it's about stress accumulation and release, and that can happen through multiple pathways. Earth has tectonics, so that's our dominant pathway. But we also have electromagnetic coupling, tidal loading, core mantle interactions, and possibly even resonance effects that span the entire planetary volume. Mars shows us what happens when you remove tectonics but keep the other factors. You still get quakes, you still get resonance, you still get mysteries, and here's the kicker. InSight detected electromagnetic signals on Mars, not Schumann resonances because Mars' ionosphere is too weak to form a stable cavity, but transient electric fields associated with dust storms and solar wind interactions. Those fields couple into the crust, just like on Earth. Whether they influence seismicity is unknown, but the mechanism exists. So when we talk about the Mode 4 signal on Earth, when we speculate about electromagnetic precursors and planetary resonance, we're not inventing physics. We're observing phenomena that show up across multiple planetary bodies. Earth isn't special. It's just the planet we've studied most. And the more we look at other worlds, the more we realise that our models are incomplete. Mars won't help us predict California earthquakes. But it reminds us that planetary interiors are dynamic, responsive, and interconnected in ways that go beyond simple mechanical models. Stress doesn't just accumulate in rock. It accumulates in fields, in fluids, in resonant modes that span entire planets. And when those modes are excited, either by internal processes or external triggers, the planet responds as a whole. InSight stopped transmitting in December 2022. Its solar panels accumulated too much dust, and it couldn't generate enough power to survive the Martian winter. But the data it collected is still being analysed, and every new discovery reinforces the same lesson. We don't understand planetary seismology as well as we thought we did. Earth is teaching us, Mars is teaching us, and if we're smart, we'll learn before the next big quake teaches us the hard way. Part 13. Can AI see what humans miss? Let's talk about pattern recognition. Humans are decent at it when the patterns are simple. Face recognition, voice identification, spotting animals camouflaged in foliage. Our brains evolved to do this quickly because survival depended on it. But when patterns become multidimensional, when they involve correlations across time and space and multiple data streams simultaneously, human intuition fails. We can't hold that much information in working memory. We can't process it fast enough. Artificial intelligence doesn't have that limitation. Modern machine learning models can ingest massive data sets, search for correlations we'd never notice, and flag anomalies in real time. And researchers are starting to apply those models to earthquake precursors, not to predict quakes, that's still out of reach, but to detect patterns that might indicate heightened risk. The basic idea is this: train a neural network on decades of seismic data, electromagnetic measurements, solar wind parameters, atmospheric pressure readings, whatever variables you think might matter. Let the AI find correlations between those variables and subsequent earthquakes. Don't tell it what to look for, just let it explore the data space and identify patterns that appear repeatedly before seismic events. Think about what that means. A human seismologist might track 3 or 4 variables simultaneously: earthquake frequency, magnitude distribution, maybe GPS measurements of ground deformation. That's already pushing the limits of what our working memory can handle, but an AI can track hundreds of variables at once: seismic amplitudes across dozens of frequency bands, electromagnetic signals from multiple stations, solar wind speed, density, and magnetic field orientation, atmospheric pressure gradients, tidal stress calculations, ocean loading effects, groundwater levels, even temperature variations in deep boreholes. Each of those variables changes constantly. Each has its own noise characteristics, its own baseline behavior, its own seasonal variations. Finding meaningful patterns in that multi-dimensional chaos is like looking for a specific constellation in a sky full of stars while the stars are moving and new ones keep appearing. Humans simply can't do it. Our brains weren't built for that kind of data space. Early results are intriguing. Some models trained on Japanese seismic data successfully identified electromagnetic precursors that human analysts had missed. Not because the signals weren't there, but because they were subtle, buried in noise, distributed across multiple frequency bands. The AI recognized them as significant because it saw the same patterns in historical data before previous quakes. One study from Kyoto University trained a deep learning model on 20 years of seismic and electromagnetic data from stations across Japan. The model learned to recognize a specific signature, a gradual increase in electromagnetic noise at frequencies between 5 and 15 Hz, combined with a slight uptick in microseismicity, occurring roughly 10 to 30 days before magnitude 5 or larger earthquakes. The signature wasn't present before every quake, but when it appeared, the probability of a significant event increased by a factor of 3. Human analysts had the same data. Some had even noticed the electromagnetic increases, but they couldn't quantify the correlation reliably because they were looking at each variable separately. The AI saw the combination, the specific timing relationship between electromagnetic and seismic changes that made the pattern predictive. Other models trained on global seismicity flagged swarm sequences that had higher than average probability of leading to larger events. Again, not with certainty, but with statistical confidence high enough to be useful. If a swarm has a 10% chance of escalating versus the baseline 2%, that's actionable information for emergency planners. The algorithm looks at swarm characteristics that humans might overlook. Not just the number of earthquakes or their magnitudes, but the spatial pattern. Are they clustering tightly or spreading out? Is the centroid of activity migrating in a particular direction? Is the rate of events accelerating or steady? Is the frequency content of the seismic waves changing over time? Combine all those factors, and you get a signature that distinguishes benign swarms from precursory ones more often than chance alone. But there's a problem. AI models are black boxes. They give you answers without showing their work. The neural network says, "This swarm is high risk." You ask why. It responds with activation patterns across millions of parameters that no human can interpret. You're left trusting the algorithm without understanding what it's basing its decision on. That's dangerous for several reasons. First, AI models can find spurious correlations. If you train a model on limited data, it might latch onto coincidences that don't reflect real physics. Second, AI can't distinguish causation from correlation. It sees patterns, but it doesn't understand mechanisms. And third, public trust requires transparency. You can't evacuate a city based on an AI's recommendation if you can't explain why the AI made that recommendation. Imagine standing in front of a city council, trying to justify a multi-million-dollar emergency mobilization. You show them the AI output. High-risk score, coloured red on the display. They ask what's driving that assessment. You explain that the neural network analysed 300 variables and identified a pattern consistent with heightened seismic risk. They ask which variables specifically. You admit you don't know. The model doesn't tell you. It just gives you the risk score. How long do you think that conversation lasts before they throw you out of the room? So researchers are working on explainable AI, models that not only make predictions but also show which input variables drove the prediction. If the model flags a swarm, it might highlight that electromagnetic signals in a specific frequency band increased by a certain amount while tidal stress was in a particular phase. That's something human scientists can evaluate and potentially verify with independent methods. One approach uses attention mechanisms, a technique borrowed from natural language processing. The AI doesn't just output a prediction, it outputs a heat map showing which parts of the input data it focused on when making the decision. If it flagged a swarm as high risk, the heat map might show that it paid particular attention to electromagnetic data from the 3 days before the escalation, combined with the spatial migration pattern of the swarm itself. That's useful. A seismologist can look at that heat map, examine those specific features, and decide whether the AI is seeing something real or hallucinating patterns in noise. It's not perfect transparency, but it's better than a pure black box. There's also the issue of false positives. AI models trained to detect precursors tend to be conservative, flagging anything unusual because missing a real event is worse than raising a false alarm. But if you're issuing warnings based on AI output, false alarms erode trust quickly. Cry wolf too many times, and people stop listening. This is the classic dilemma in signal detection theory. You can tune your model to be sensitive, catching most real events but also flagging lots of false positives, or you can tune it to be specific, minimizing false positives but missing some real events. You can't optimize both simultaneously, there's always a trade-off. For earthquake early warning, the trade-off leans towards sensitivity. Better to warn about 10 swarms where 9 turn out to be nothing than to miss the one that leads to magnitude 7. But that calculus assumes warnings are low cost. If each warning triggers expensive emergency responses, or if false alarms cause public panic, the cost-benefit calculation shifts. Despite those challenges, AI is already contributing. Several research groups used machine learning to analyze the December 19th data. One model flagged the Mode 4 signal hours before human analysts noticed it. based on deviations from baseline Schumann resonance behavior. Another model correlated the signal timing with solar wind parameters and predicted elevated seismic risk for the Bay Area. It didn't predict a specific quake, but it correctly identified the swarm escalation as anomalous. The model that flagged the Mode 4 signal used an anomaly detection algorithm trained on 2 years of continuous Schumann resonance data. It learned what normal variation looks like, accounting for daily cycles, seasonal changes, and the random fluctuations driven by global lightning activity. When the December 19th signal appeared, the algorithm immediately recognized it as outside the normal range. Not just unusual, but statistically significant at the 99.9% confidence level. A human analyst looking at the same data might have noticed something odd. But how do you quantify odd? How do you distinguish genuinely anomalous from merely surprising? The AI doesn't rely on intuition. It calculates probabilities, and when the probability drops below a certain threshold, it raises a flag. Could AI have prevented disaster if the swarm had triggered a magnitude 7? No. But it could have moved the needle on preparedness. A few extra days of warning, even probabilistic warning, allows first responders to stage resources, utilities to inspect infrastructure, and residents to review emergency plans. That's not trivial. Think about what a few days means. Hospitals can discharge non-critical patients, creating bed space for potential casualties. Fire departments can pre-position heavy rescue equipment. Water utilities can inspect vulnerable pipelines and shut off sections that are most likely to rupture. Schools can move emergency supplies from storage to accessible locations. Families can check their earthquake kits, review evacuation routes, make sure their gas shut-off wrenches are where they're supposed to be. None of that prevents the earthquake, but all of it reduces casualties and speeds recovery. That's the realistic promise of AI-assisted earthquake monitoring, not prediction in the sense of telling you when and where, but risk assessment that lets you prepare more effectively. The future likely involves hybrid systems. AI detects anomalies in real time and flags them for human experts. The experts evaluate whether the anomaly reflects known physics or is likely spurious. If it passes that filter, it goes to decision-makers who weigh the cost of action versus inaction. It's not perfect, but it's better than relying on human intuition alone or blind trust in algorithms. You could imagine a system where AI monitors all available data streams continuously. When it detects an anomaly, it generates a report summarizing what it found, which variables contributed most to the assessment, and what historical precedents exist for similar patterns. That report goes to a seismologist on duty, who reviews it, runs additional analyses if needed, and either dismisses it as a false alarm or escalates it to emergency management. The key is keeping humans in the loop. AI handles the impossible task of monitoring hundreds of variables across dozens of stations continuously. Humans provide the judgment about whether the AI's findings make physical sense and whether the risk level justifies action. But we need more data. AI models improve with training examples, and we don't have many examples of major earthquakes with complete, multi-parameter monitoring. Each new quake adds information, refines the models, reduces uncertainty. The December 19th event is valuable precisely because we have electromagnetic, seismic, and solar data all converging. That's rare. Most earthquakes occur with incomplete monitoring. Maybe we have good seismic data but no electromagnetic measurements. Maybe we have electromagnetic data but the nearest station was too far away to detect precursors. Maybe the event happened before certain types of sensors were deployed. Every incomplete dataset is a missed opportunity to train better models. That's changing slowly. More sensors are being deployed. Data sharing is improving. Archives are being digitized. In another decade, we'll have a much richer training dataset, and the AI models that learn from that dataset will be correspondingly better at recognizing precursory patterns. There's an ethical dimension too. If AI identifies a high-risk period and authorities choose not to act, are they liable when disaster strikes? Conversely, if they issue warnings based on AI recommendations and nothing happens, who's responsible for the economic disruption? These aren't technical questions. They're societal questions that we haven't figured out yet. The legal framework for AI-assisted decision-making is still being developed. If a doctor uses AI to help diagnose cancer and the AI is wrong, who's liable? The doctor for trusting the AI company for providing flawed recommendations, the hospital for implementing the system. Courts are still working this out. Earthquake warnings face the same questions. If emergency managers follow AI recommendations and evacuate a city unnecessarily, they'll face political and legal consequences. If they ignore AI recommendations and people die, they'll face different consequences. There's no safe choice, only choices with different risk profiles. But the technology is advancing faster than the policy. AI models are getting better, cheaper, more accessible. Soon, independent researchers, even amateurs, will be able to run their own earthquake risk assessments using publicly available data and open-source machine learning tools. That democratizes earthquake science, but it also creates potential for misinformation. Imagine a panic triggered by an AI model that someone misinterpreted or intentionally misrepresented. YouTube could be flooded with videos claiming that AI predicts a magnitude 8 earthquake next Tuesday. The model might actually be saying there's a 3% elevated risk over the next 3 months, but that nuance gets lost in the headline. People panic. They withdraw money from banks, they flee the city, and when nothing happens, trust in both AI and earthquake science takes a hit. So we need frameworks, standards for AI in seismic risk assessment, guidelines for interpreting model outputs, public education about what AI can and can't do, and most importantly, humility. AI is a tool, not an oracle. It sees patterns we miss, but it doesn't understand the planet the way a geophysicist does. The best results will come from collaboration between human expertise and machine intelligence, each compensating for the other's weaknesses, and when the next mode 4 signal appears, when the next swarm accelerates, the AI will flag it. The question is whether we'll listen, whether we'll have the institutional structures in place to evaluate the flag appropriately, whether we'll have the courage to act on probabilistic information, whether we'll be able to communicate uncertainty to the public without causing panic or complacency. Those are the challenges that will determine whether AI becomes a valuable tool for earthquake preparedness or just another source of noise in an already confusing landscape. Part 14. Quantum Sensors and the Low-Frequency Frontier. Now we're getting into the cutting edge, the speculative future, technology that exists in labs but hasn't deployed globally yet. I'm talking about quantum sensors, devices that exploit quantum mechanics to measure things that classical sensors can't. Traditional magnetometers work fine for most applications. They measure magnetic field strength using coils of wire or specialized materials, but they have limitations. At very low frequencies, below 1 Hz, the signal-to-noise ratio degrades. Thermal noise, instrumental drift, and environmental interference swamp the measurement. You can't reliably detect weak magnetic variations at the frequencies where planetary resonance and crustal stress might matter. Quantum magnetometers are different. They use atoms, typically rubidium or cesium, as the sensing element. Shine a laser at the atoms, put them in a magnetic field, and their quantum states respond in measurable ways. The sensitivity is absurd. These devices can detect magnetic field changes as small as a femtotesla, which is about 1 quadrillionth of Earth's background field. Think about that for a moment. Earth's magnetic field at the surface is roughly 50 microtesla. A quantum sensor can detect changes a billion times smaller than that. It's like being able to hear a whisper in a stadium full of screaming fans, except the stadium is the entire electromagnetic environment of the planet, and the whisper is the charge building in rocks deep beneath California. Why does that matter? Because it opens up the low-frequency frontier, processes that generate weak magnetic fields slowly, like charge accumulation in the crust or electromagnetic resonances in the Earth ionosphere cavity, become detectable. Suddenly you can map stress fields not just seismically, but electromagnetically. You can see precursors that were invisible before. Several research groups are experimenting with quantum magnetometers deployed near active faults. The idea is to create a network that monitors magnetic field variations continuously, looking for anomalies that correlate with seismicity. Early tests in Japan and Italy show promise. The sensors detect variations that classical magnetometers miss entirely. Whether those variations predict earthquakes remains to be seen, but the data is compelling. In Japan, researchers placed quantum sensors along the Nankai Trough, a subduction zone that's overdue for a massive earthquake. The sensors picked up magnetic field variations that occurred days before small swarm sequences. Not every variation led to quakes, but every quake was preceded by variations. That's the kind of pattern that makes you pay attention, even if you're skeptical. Italy's deployment focused on the Apennines, a region with frequent moderate earthquakes. Same story. Magnetic anomalies before seismic activity. The timeline varied from hours to weeks, which makes prediction impossible but monitoring valuable. If you know that magnetic variations often precede ruptures, you can increase readiness when those variations appear. Not evacuation, but preparation. There's also talk of satellite-based quantum sensors. Put them in orbit, and you get a global view of electromagnetic activity across the entire planet. No gaps in coverage. No reliance on ground stations that might be in the wrong place. Every fault system, every tectonic boundary, monitored simultaneously. The data volume would be immense, but AI could handle it. Flag anomalies. Correlate with seismic networks. Provide probabilistic risk assessments in real time. The European Space Agency has proposed such a mission, a constellation of satellites equipped with quantum magnetometers, orbiting in coordinated patterns to map Earth's magnetic field with unprecedented resolution. The goal isn't just earthquake monitoring, it's understanding planetary-scale electromagnetic processes. But earthquake applications would be a major benefit. Imagine what that would mean for December 19th. Instead of a handful of ground stations detecting the Mode 4 signal, you'd have continuous global coverage. You'd see exactly where the electromagnetic anomaly originated, how it propagated, whether it coupled into the ionosphere uniformly or showed regional variations. You'd have context that's completely missing from current data. But quantum sensors have problems. They're fragile. They require precise environmental control, temperature fluctuations, vibrations. Even stray magnetic fields from power lines can throw off the measurements. Deploying them in harsh field conditions is challenging, and they're expensive. A single quantum magnetometer costs tens of thousands of dollars. Outfitting a global network would run into hundreds of millions. The engineering challenges are significant. Quantum sensors work by maintaining atoms in carefully controlled quantum states. Any disturbance, thermal or mechanical or electromagnetic, collapses those states. In a laboratory, you can shield the sensor, stabilize the temperature, eliminate vibrations. In the field, next to a busy highway or on a mountainside exposed to weather, those controls become nearly impossible. Some researchers are working on ruggedized designs. Compact sensors that can operate in wider temperature ranges, tolerate more vibration, self-calibrate to account for environmental drift. Progress is happening, but slowly. The trade-off is always sensitivity versus robustness. Make the sensor tough enough to survive in the field, and you sacrifice some of the quantum advantage that made it appealing in the first place. There's also the interpretation problem. Just because you can measure something doesn't mean you understand what it means. Quantum sensors will detect all kinds of magnetic variations: lightning, solar wind, power grid harmonics, crustal stress, magma movement. Separating signal from noise requires sophisticated models that we haven't fully developed yet. Every urban area generates electromagnetic pollution. Power lines create 50 or 60 Hz signals depending on your grid frequency. Electric trains, industrial equipment, even the slow drift of conductive groundwater all produce magnetic signatures. A quantum sensor near San Francisco would be swimming in anthropogenic noise. Filtering that out to find the geological signal underneath is a massive computational challenge. Machine learning helps. Train a model on what normal electromagnetic activity looks like in a given location, accounting for daily and seasonal variations, human activity patterns, weather effects, then flag deviations from that baseline. But you're still making assumptions about what's signal and what's noise. If crustal stress produces magnetic variations that look similar to industrial interference, the model might dismiss them as artifacts. And then there's the quantum entanglement angle. This is where things get really speculative, bordering on science fiction. Some researchers hypothesize that if crustal stress generates charge through piezoelectricity, and that charge creates electromagnetic fields, then those fields might influence quantum states in the rocks themselves. If you had sensors that could detect quantum coherence in geological materials, you might see precursors at a level that's completely invisible to classical physics. The idea is that minerals with magnetic properties like magnetite might maintain quantum correlations across macroscopic distances when subjected to stress. Those correlations would manifest as subtle changes in magnetic field geometry that quantum sensors could detect. It's like the rocks are communicating through quantum channels before they fracture mechanically. Is that real? Nobody knows. Quantum effects in macroscopic systems are controversial. Most physicists would say that thermal noise destroys quantum coherence long before you get to anything geologically relevant. At room temperature, with thermal energy constantly jostling atoms, quantum states collapse almost instantly. Coherence times are measured in nanoseconds for most materials, far too short for geological processes that unfold over hours or days. But a minority argues that certain minerals, particularly those with magnetic properties, might sustain quantum correlations over macroscopic distances. If true, it would revolutionize geophysics. If false, it's just noise. The experiments to test this are difficult because you need to isolate quantum effects from all other sources of magnetic variation. Nobody's succeeded yet, but the theoretical possibility remains open. Military and intelligence agencies are interested in quantum sensors for different reasons. Submarine detection, underground bunker mapping, surveillance. The same technology that could monitor earthquakes could also monitor human activity. That raises ethical questions about dual-use technology and whether civilian research should accept funding from sources with non-civilian applications. A quantum magnetometer sensitive enough to detect crustal stress is also sensitive enough to detect submarines moving underwater or vehicles driving through tunnels. The magnetic signature of a steel hull displaces Earth's field in measurable ways. Deploy a network of these sensors, and you have a surveillance system that's nearly impossible to evade. That's why some quantum sensor research is classified. That's why civilian researchers sometimes find their grant proposals rejected without explanation. The technology has strategic value, and governments don't want it proliferating freely, which creates a tension between scientific openness and national security. How do you advance earthquake monitoring without also advancing military capabilities? But let's assume the technology matures. Let's assume quantum sensors become cheap, robust, and deployable at scale. What happens then? We'd have unprecedented visibility into Earth's electromagnetic state. We'd see precursors we can't see now. We'd detect patterns that are currently invisible. And we'd face a new problem. What to do with that information? Because seeing a precursor doesn't mean you can predict the timing or magnitude of the subsequent quake. It just means you know something is building. Do you issue warnings based on that? Do you evacuate cities for days or weeks while you wait to see if the precursor develops into rupture? Or do you stay silent, monitor closely, and hope for the best? These aren't technical questions. They're societal, political, ethical questions. And we don't have good answers yet. We're advancing the technology faster than the framework for using it responsibly. Quantum sensors will arrive before we've figured out what to do with the data they provide. Imagine the scenario. Quantum sensors along the Hayward Fault detect a magnetic anomaly consistent with stress accumulation. The pattern matches what was observed before previous major quakes in other locations. AI models estimate a 30% probability of a magnitude 6.5 or larger event within the next 2 weeks. What do? Evacuate Oakland and Berkeley. 2 million people, leaving their homes for potentially weeks based on a 30% chance. The economic cost would be billions. Businesses would close, schools would shut, and if nothing happens, public trust in science collapses. But if you don't evacuate and the quake hits, thousands could die. You'd be crucified for ignoring the warning. That's the impossible choice quantum sensors might force on us. Better information doesn't always make decisions easier. Sometimes it just makes the stakes more visible. But they're coming. Research labs are refining them. Prototypes are being tested in the field. And within a decade, we'll have sensor networks that make today's instruments look like stone tools by comparison. When that happens, when we can finally see the electromagnetic scaffolding that supports seismic activity, we'll enter a new era of earthquake science. Whether that era leads to better forecasting or just more confusion depends on what we learn. The sensors will reveal the data. Understanding what it means is still up to us. And the Earth, as always, will keep its secrets until the moment it decides to let them go. Part 15. The question. We're not ready to answer. So here we are. 15 parts. 15,000 words. And if you're still with me, you've followed the chain from an interstellar object passing by, to electromagnetic signals, to swarms under California, to locked faults, storing decades of strain energy. You've seen the precedents, the patterns, the correlations that might mean something or might mean nothing. You've watched as science bumps up against its own limitations, refusing to commit to conclusions because the data isn't quite there yet. Let me summarize what we know. On December 19th, 2025, 3I Atlas made its closest approach to Earth. At that exact moment, a mode 4 Schumann resonance signal appeared, clean and strong and persistent, in a way that doesn't happen naturally during normal conditions. Hours later, a seismic swarm beneath the Bay Area accelerated dramatically, releasing 1/3 of its total energy in a single night. Beneath it all, the Hayward Fault sits locked, storing a century and a half of strain, waiting for the moment when friction can no longer hold. What we don't know is whether those events are connected. We don't know if Atlas triggered the signal, or if the signal triggered the swarm, or if all of it is coincidence layered on coincidence. We don't know if the electromagnetic precursors we've detected before other major quakes reflect real physics or just observer bias. We don't know if planetary alignments matter, if solar wind matters, if quantum effects matter. We have correlations, we have hypotheses, we have models that fit some of the data some of the time, but we don't have certainty. And that's the uncomfortable truth. Science is supposed to give us answers, but sometimes it just gives us better questions. Right now, the question is this. What if the planet already answered on December 19th, and we just didn't like what it said? What if the mode 4 signal wasn't random? What if it was the Earth's way of announcing that stress has reached a critical level, that the electromagnetic environment has shifted into a precursory state? What if the swarm was the first domino falling in a sequence that leads eventually to a magnitude 7 rupture? Not tomorrow, not next week, but soon, on geological timescales which are slower than human ones, but on human timescales which are faster than we want to believe. The thing about earthquakes is that they don't announce themselves with fanfare. There's no countdown timer, no alarm bells. Just a series of small changes that might be meaningless, or might be everything. A swarm that could dissipate harmlessly, or could be the opening act. An electromagnetic signal that could be atmospheric noise, or could be the crust screaming. And we're left standing in the middle, trying to decide which interpretation keeps us safer. The danger of dismissing weak signals is that you miss the warning. You convince yourself that because nothing exploded on December 19th, nothing happened at all. You move on with your life, reassured by the silence. But the Earth doesn't work that way. It doesn't explode on schedule. It accumulates. It builds. And when it finally releases, the signs were there all along, scattered across datasets that nobody thought to connect. History is full of these missed warnings. The 2004 Sumatra earthquake killed over 200,000 people. Scientists knew the Sunda megathrust was capable of magnitude 9 events. They knew it was overdue. But there was no warning system in place because the political will to fund one didn't exist until after the disaster. The warning signs were geological, visible in the rock record, but nobody connected them to imminent risk. The 2011 Tohoku earthquake in Japan was similar. Japan had the best earthquake monitoring in the world, but the magnitude 9.1 still surprised everyone. The assumptions about maximum possible magnitude were wrong. The recurrence intervals were wrong. And when the earthquake hit, followed by a tsunami that killed nearly 20,000 people, the question everyone asked was, why didn't we see this coming? The answer is that we did, and we didn't. The data was there. Paleoseismic evidence showed that magnitude 9 events had occurred before on that fault, but the instrumental record only went back a century, and nothing that large had happened in living memory. So the models assumed it couldn't happen, and when it did, the word everyone used was unprecedented, but it wasn't unprecedented. It was just rare enough that we'd convinced ourselves it was impossible. The danger of overreacting is different, but equally real. You panic. You evacuate. You disrupt millions of lives based on a signal that might be noise. False alarms destroy credibility. They erode trust in science and institutions. And when the real warning comes, nobody listens because they've heard it before and nothing happened. Italy learned this lesson the hard way. In 2009, a major earthquake struck L'Aquila, killing over 300 people. In the months before, there had been a swarm of small quakes. Some local researchers claimed it was a precursor and warned of a larger event. Government scientists convened, reviewed the data, and concluded the swarm didn't indicate heightened risk. They told people to stay calm, to remain in their homes. Then the magnitude 6.3 hit. Afterward, those scientists were prosecuted for manslaughter. The charge was essentially that they'd provided false reassurance, causing people to stay indoors who might have survived if they'd been outside or evacuated. The convictions were later overturned on appeal, but the damage was done. Scientists around the world took note. Speak up about earthquake risk, and you might be sued if you're wrong. Stay silent, and you might be prosecuted if something happens. The legal framework creates paralysis. So what do? We watch, we instrument, we analyse, we treat every anomaly as potentially significant without jumping to conclusions. We build frameworks for interpreting weak signals probabilistically, acknowledging uncertainty while still respecting the possibility of risk. We train AI models to detect patterns we'd miss, while maintaining human oversight to filter spurious correlations. We deploy quantum sensors to see electromagnetic precursors more clearly, while developing ethical guidelines for what we do with that information. But all of that takes time, funding, political will, and most importantly a cultural shift in how we think about prediction versus preparedness. We can't predict earthquakes, in the sense of saying, magnitude 6.5 will strike this location at this time. But we can identify periods of elevated risk. We can recognise when multiple factors align in ways that historically preceded ruptures, and we can communicate that probabilistically to the public. The problem is that humans don't think probabilistically. We think in binaries. Will it happen, or won't it? Should I worry or shouldn't I? A 30% chance of a major earthquake in the next month sounds alarming or dismissible depending on your risk tolerance. Some people evacuate, some people stay, and when the month passes without incident, the ones who evacuated feel foolish, while the ones who stayed feel vindicated. Until the earthquake hits 2 weeks later and everyone's calculus flips. And we remember that the Earth has its own timescale. It doesn't care about news cycles or budget deadlines or political elections. It operates on the rhythm of tectonic plates grinding past each other, stress accumulating atom by atom, charge building in crystalline lattices deep underground. That rhythm is slow until it's suddenly fast. And when it shifts from slow to fast, the transition is often marked by signals that seem insignificant until you look back and realise they were anything but. Geologists talk about this as the concept of a critical state. A system near critical doesn't respond linearly to perturbations. Small inputs can trigger massive outputs. A sand pile near critical angle will avalanche if you add one more grain. A fault near failure will rupture if you add one more megapascal of stress. The challenge is knowing when you're near critical versus when you've got plenty of margin left. December 19th might have been that transition. Or it might not. The data doesn't tell us which yet. But the question hangs there, unanswered and maybe unanswerable until the fault decides for itself. Was it the trigger? Was it the ignition? Or was it just another day on a planet that's been quaking for 4.5 billion years, long before we showed up to measure it? What we do know is this. The Hayward fault will rupture. Not if, when. And when it does, people will ask why we didn't see it coming. They'll ask why the warning systems failed, why the buildings collapsed, why we weren't prepared. And the answer might be that we saw it. We saw the mode 4 signal, we saw the swarm, we saw the electromagnetic precursors and the solar wind coupling and the planetary alignment. We saw all of it. We just didn't know what we were looking at. Or maybe we did know. Maybe some researchers flagged it. Maybe the data was shared in the right circles, analysed carefully, understood correctly, and maybe the decision was made that the risk wasn't high enough to act on, that the cost of false alarm exceeded the benefit of preparation, that uncertainty justified inaction. That's not negligence. That's the reality of making decisions with incomplete information. Every day, emergency managers and government officials make these calculations, issue a hurricane evacuation warning based on forecast models that might be wrong, warn about a terrorist threat based on intelligence that might be false, close schools because of a pandemic that might fizzle out. Every choice has consequences, and hindsight always judges harshly. I can't tell you which version is true. I can tell you that the Earth is a complex system with feedback loops we don't fully understand. I can tell you that electromagnetic coupling between the crust and ionosphere is real, even if the mechanism isn't proven. I can tell you that interstellar objects carry energy and charge and mystery, and dismissing them as irrelevant is premature. I can tell you that AI is starting to see patterns we can't, and quantum sensors will soon reveal electromagnetic landscapes that were invisible before. But I can't tell you when the fault will slip, and neither can anyone else. That's the frustration and the fear wrapped together. We have all this technology, all this data, all these brilliant minds working on the problem, and still the planet surprises us. Still, the earthquake comes when we don't expect it, or doesn't come when we're sure it will. Still, we're left guessing. So what's the takeaway? Pay attention, not to doomsday predictions or fear-mongering, but to the quiet signals that don't make headlines, the mode 4 spikes, the swarm accelerations, the solar wind disturbances, the planetary alignments. Individually, they mean little. Together, they might mean everything. And ask yourself this. If the Earth is trying to tell us something, are we listening? Or are we so convinced that we know better, so confident in our models and our assumptions, that we've stopped hearing the planet's voice? Because the Earth will speak regardless of whether we're listening, and when it does, the conversation ends. What's left is just response, emergency, aftermath, grief. Maybe December 19th was nothing. Maybe it was the calm before. Maybe we'll look back in 6 months and laugh at how worried we were, how we connected dots that didn't connect, how we saw patterns in randomness. I hope that's true. I genuinely do. But if it's not, if the mode 4 signal was real, if the swarm was precursory, if the Hayward is primed and the alignment in January pushes it over the edge, then we'll have to reckon with what we missed, not because the data wasn't there, but because we chose not to believe it. The planet already answered. We just haven't decided yet whether we like what it said, and that indecision, that hesitation between dismissal and alarm, might be the most human response of all. We're creatures caught between our desire for certainty and our tolerance for ambiguity. We want to know what's coming, but we're terrified of being wrong, so we wait. We watch the seismometers. We monitor the electromagnetic spectrum. We track the planetary alignments. We let the AI models run their calculations. And we hope that when the answer finally arrives, we're ready for it. Because ready or not, the Earth keeps its own schedule, and December 19th might have been the moment it penciled in our appointment.